All right, guys, page 23 in your packets. Hey, so we're starting the next section, sketching a curve. It is the next section, but it's not going to feel like a new topic because we're just putting everything together, gathering all the information that we can from the function level, from the f prime level, from the f double prime level, and we're gathering all that information so that we can get a fuller picture of what the real graph looks like. Okay, so really we're just putting it together, nothing new, but we just haven't had a chance to see how they all are connected with each other. Okay. So number one says sketch a graph of the function and find the below information. We're starting off with an easier function here. This is a polynomial. So polynomial is easier in the sense that there are no vertical asymptotes, there are no horizontal asymptotes, but we can find x-intercepts and y-intercepts at the function level. So at the function level, before the derivatives, we can gather information about certain points, such as the x-intercept. Okay. To find the x-intercept, we're just basically setting the function equal to 0, or basically replace y with 0 and then solve for x. So we're trying to find x-intercept. We want to solve for x. I'll look for an x value. So that means y is going to be 0. All right, so if I replace 0 in for y, solve for x, I can factor out x cubed, negative 3x squared plus 5. If I solve for x, x cubed equals 0, that's just going to be 0. That's going to be the origin. If I set negative 3x to the fifth plus 5 equal to 0, sorry, x squared, negative 3x squared plus 5 equals 0, I get x squared equals negative 5 over negative 3, which is 5/3. If I take the square root of that, I get plus or minus square root of 5/3, which is going to end up being 1 point something. Okay, so we can use our calculator to find it's around like 1.1, 1.2-ish. It just helps anchor our graph. We know that our graph is going to be along those points. And then if I want to find the y-intercept, that means I want to solve for y. If I have to solve for y, my x is 0. Replace x with 0. So I get y is equal to 0 plus 0, which is 0. So x and y-intercept are the same. They're both 0, 0. So at the end, we can plot those points and have the graph go through those points. Now, if I want to gather information about increase, decrease, relative max, relative min, that's all going to come from the f prime level. So let's go ahead and find f prime. We'll create our slope sine line. We'll basically do our first derivative test and gather all the data that we can from the f prime level. Okay, try that. So treat this like going through first derivative test. We have test points. Oh, sorry, I forgot about 0. 0 is a critical point too. So I'm testing -2, -1/2, 1/2, and 2. These are all points that I found in each of the subintervals. Plug it into your derivative function, and then gather the signs. -2, I get 1 minus 4. That's negative times positive, which is negative. Plug -1/2, I'll get positive times negative, which is, sorry, positive times positive, which is positive. Plug 1/2 in, I'll get the same thing, positive. Plug 2 in, I'll get negative. So based off of this, we can tell what we relative extrema, right? There's a relative min at minimum at -1. There's neither at 0 because the graph is going to rise, it's going to flatten out, and then continue rising. And then hits a slope 0 at 1, increase, decrease, which means a relative max. So the arrows kind of gives us the path of our graph. Okay, let's move into second derivative function. This will give us, basically we'll go through test for concavity, and we'll find the curvature of each of these subintervals. Okay, F double prime, power rule again to get to the second derivative function. All right, this is around 0.7, so I'll choose -1, I'll choose -1/2, I'll choose 1/2, I'll choose 1. Into the second derivative function. So I'm going to get a negative times a negative, so 2 negatives makes positive. Concave up. Plug -1/2, I get negative times positive, which is negative, so concave down. Plug 1/2, positive times negative. Positive times negative, positive. Positive times positive, positive. Plug 1 in, positive times negative is negative. So what can we conclude about these points here? These are all what? Points of inflection, because why? change in signs, right? So it's not strong enough of an argument to say that f double prime is equal to 0. That's part of it, but it also needs to change signs. So we have to make sure that we establish that hey, there's no change in signs, there's no point of inflection. We can find all these y values by plugging into the original function. The more important thing is to find the y values of the relative max, relative mins. Okay. So if I plug -1 into the function, I can get those y values. So let me just do that here. We're expecting a relative min at -1 here. So relative min is at -1. Plug -1 into the function here. So -3 plus 5, that's a nice easy number, -1 comma 2. Relative -1 comma, wait, is that -2 here? Sorry, 3 minus 5, that's -2. Okay, relative max, the arrows indicate that there's a relative max at x equals 1. Plug 1 into the function, -3 plus 5 is 2. Back with x-intercept, this is around 1.3 plus or minus 1.3. Okay, so I'm just going to highlight some of these points here. 1, 2, -1, -2. I'm just going to estimate these points here. So these are x-intercepts. So plus or minus 1.3, somewhere here. And also 0, 0, right? So that's nice to have 3 anchor points along the x-axis. We know there's a relative min at -1, -2. There's a relative max at 1, 2. Okay. Basically, if you look at these points, if you just connect the dots, you basically have the graph. But we'll follow these arrows here. I like to do this in 2 drafts. It just feels like a lot to try to do everything at once. So I'm going to lightly just sketch out the path of my graph, and then I'll retrace the path with more detailed curvature once I get the path down. So all right, so we know our graph is going to be decreasing until we hit a relative min at -1. The graph is going to rise. Now that is not a relative max, relative min, but it is a slope 0. So we want to make sure that we can get our graph to kind of level off for a moment here, and then continue increasing, hits a relative max, decrease, x-intercept, and continues to decrease. So I'm just going to sketch the graph. This is not the final product, but at least I want to kind of have something to build off of. Okay, so I'm just going through the points I've established, and I'm following the path of the arrows. Okay, any questions there? To make it a little bit easier on ourselves, let's just have our points of inflection go through the path of the graph. So we're going to highlight these points here. So wherever the graph lands, this is around like at -0.7 and 0.7. Go ahead and highlight those points. So estimate where you think -0.7 is. Highlight that point. Estimate where 0.7 is, wherever the graph lands. Fill that point. And then we also want to fill in 0. These are our target points. And these are the points where we want our curvature to change. So this is where I estimate -0.7 to be on my graph. X value somewhere between 0 and 1. I just see where that graph lands between 0 and 1. That's around, not the y value 0.7, just the x value of 0.7. Okay, so now I'm going to retrace the graph and just follow the curvature that I need. I want concave up. up until this first point of inflection. So I'm going to kind of over exaggerate the curvature here. So concave up. At this point of inflection, it's going to switch over to concave down. So I'm going to give it that concave down shape between these 2 points. Switch back to concave up. And then finish off with concave down. Any questions here? So we see how the function, the derivative, the second derivative, they all contribute information with this final picture that we see in front of us. I mean, it's not perfectly accurate, but it is a lot of detailed information about the graph. From the original function, we gather information about order pairs, x-intercepts, y-intercepts. There are no horizontal or vertical asymptotes, but if there were denominators, then that will help give us the shape of our graph or give us some boundaries for our graphs. At the derivative level, we're able to gather information about where the graph is rising, where the graph is falling, where the relative max, relative mins are. And at the second derivative level, we're able to gather information about how is the curve changing? How is the curvature changing along the path of this graph? So they all get put together onto the same graph. Function, f prime, f double prime, they all contribute some information to the graph that we see in front of us. All right, next page. We may not finish this problem, but it's okay. Whatever we don't finish, we can pick up after a break. But I just want to get started with this, and but I'm going to save some time at the end for us to continue reviewing for our quiz tomorrow. So this one is a little bit more involved because there's a denominator here. So we know denominator contributes information about our vertical asymptotes. But the same idea as before, if I want to solve for x, I can find x-intercept, right? Replace y with 0, solve for x, I'll find my x-intercept. Replace x with 0, solve for y, I can find y-intercept. So x-intercept means I want to solve for x. So I'm going to replace y with 0. Now, whenever you have a numerator and denominator, you basically just need to set the numerator go to 0. We know the numerator go to 0 gives us x-intercept. Denominator go to 0 gives us vertical asymptote. So numerator go to 0, we're just going to get x equals 0, which is just 0, 0. So I can just go ahead and fill that point in. Y-intercept, if I see 0, 0, then y-intercept is also 0, 0 because the origin is the intersection of the x and the y axis. All right, next up, the denominator is where we can find vertical asymptote information. So I'm going to set the denominator equal to 0. So we have 2 vertical asymptotes, plus or minus 3. The nice thing about asymptotes is that it gives us boundaries for our graph, and we know that our graph is just naturally going to gravitate towards the asymptote. So we kind of have an idea how the graph is going to be shaped by these asymptotes. Another thing that we can gather is horizontal asymptotes. So horizontal asymptotes is where we take the limit as x approaches infinity, right? Which is basically comparing degrees. So if we compare degrees are the same, 2 over -1. The horizontal asymptote is at y equals -2. Again, the asymptotes is really just for exiting the graph. It's not going to be something that is going to prevent the graph from crossing. So really, the dotted line is just for the edges, for the outer regions of the graph. It's not really for the middle of the graph. All right, so I think we've gathered as much information as we need to from the function level, x-intercept, 2 vertical asymptotes, y-intercept, horizontal asymptote. So now let's move into f prime. Now, if I want to do f prime, what rule do we have to go through? Quotient rule, yeah. Okay, f prime g minus f g prime all over g squared. So as we build our f prime, just continue to keep in mind that your denominator, once you go through quotient rule, your denominator is like 90% of the time, it's not going to change. Okay, so we don't want to do any cleanup with the denominator. Denominator is pretty much set. It's really just a numerator we have to worry about. Okay, so don't try to do too much with the denominator. You may be tempted to want to FOIL or expand, but having those parentheses there, it's a good spot for our next step. So once we get to f prime, we want to look for critical points. Critical points comes from both the numerator and denominator. So my numerator will give me 0. My denominator will give me plus or minus 3. So we're going to place them onto our slope sign line. Now, notice that -3 and 3 are vertical asymptotes, but they still end up on the f prime sign line. Not because it has a chance of being a relative max, relative min, but it does help separate our intervals of increase and decrease. So the arrows kind of help indicate to us that there is a relative minimum at 0, because we do have an ordered pair 0, 0 that's sitting on the graph. So we expect the graph to have a relative min at 0, but then around -3 and 3, the graph is just going to be moving towards the asymptote. Okay, f double prime. To get to the second derivative, what rules do we have to go through? Chain rule and what? Quotient rule. Which rule comes first? Quotient, because the parentheses is not over everything, right? We want to apply the rule that has a further reach. The parentheses is only over the denominator, so that's just going to be the chain rule is only for the denominator, but quotient rule is for the entire problem. So we start with quotient rule first. So f prime g minus f g prime all over g squared. Now, once you get to g prime, then chain rule gets activated. And f prime, 36x becomes 36. G is my entire denominator minus f, that's my numerator, and then my g prime is where I got to do chain rule. So chain rule is outside times inside derivative, right? So the outside is the parentheses squared, and the inside is the 9 minus x squared. So we're taking turns with each derivative. parentheses squared becomes 2 parentheses to the first power. 9 minus x squared becomes negative 2x. So all this is my g column. All of my denominator squared. Okay, if we keep going, we will be able to clean this up. And then once we clean it up, we can set the numerator and denominator to 0, create our second derivative sign line, populate our concavity sign line, and then determine concave up, concave down, and then we put it all together. I want to finish this up after break because we have time after that, but at least I want to get started. We're just want to show you that this section is really not anything new. We're just putting it all together with a function, derivative, and second derivative to help contribute to see how they form the information about the curve. Let's shift over to more quiz review for tomorrow. I know this is your homework, but I do want to just talk a bit about number 8 from your homework. This is on page 6. Just to make sure that you guys are comfortable with sketching the graph. So the first statement is just a bunch of ordered pairs. We can plot them when you're ready to sketch your graph. The second statement gives us some helpful information about our f prime sign line. So this first statement says f prime of x is less than 0. That's going to be negative slope to the left of 2 and to the right of 4. Right, negative slope. F prime of 2 does not exist. That can mean a few different things. It could mean sharp turn, could be vertical tangent, could mean vertical asymptote, could mean a hole. F prime of 4 is equal to 0. That is indicating that there's a slope 0 at 4. F prime of x is greater than 0. Positive slope between 2 and 4. So we kind of get a picture as to how our graph is forming. F double prime of x is less than 0. That's concave down. Or x doesn't equal to 2. That means everywhere except 2. So here's my graph. Bunch of ordered pairs. 0, 4. 6, 0. 2, 0. And 4, 2. If I do this in 2 stages, my graph is going to decrease to a relative min at 2, increase to a relative max at 4, and decrease past that. That's my overall path of the graph. When I retrace it, I'm not going to veer too far from this path. Now, here, I'm going to make this a sharp turn to make the slope not defined. But here, I'm going to round out the curve at 4 because I want to slope 0 at 4. So I do want my graph to be smooth. And then all the way through, my graph is going to be concave down. So it's only going to show concave down. So maybe something like this. So concave down, hits a sharp turn, make it a sharp turn, but I'm going to round out the top of my graph to be slope 0, but I'm still maintaining concave down all the way through. Now, why can I not do a full concave down shape and continue like this? What's wrong with me continuing and shaping that full concave down shape? It's decreasing, right? I got to keep it along this path here. I can't let it go past to a slope to, it's always decreasing. I can't let it change direction. Okay, so it's got to kind of just follow along that curve there because of this behavior. Okay, I also want to talk about let me call this 8B here. I don't know if you have room, but or you can just kind of watch along here. I want to spell out how these curves, portions of this curve have different combinations of slope and concavity. So let's start off with this first piece here. What can we say about f prime in this first region? F prime is what? What f prime is slope? What's the slope here? Positive, so it's greater than 0. But f double prime is what? Yeah, because why? It's concave down, right? So if the problem asks you, what does the graph look like if slope is positive and concave down? This is the portion of the graph that you would create. F prime can also look like this. F double prime can also look like this. All right, different notations for F prime and F double prime. Let's move on to this next part here. This portion of the graph, how would you describe the slope and the concavity? Or slope, F prime and F double prime. F prime is less than 0. F double prime is still less than 0, right? Still concave down. All right, next stage. What about this? dy dx, or f prime is negative slope. d2y over dx2, that's same thing as f double prime is greater than 0 because concave up, right? Kind of has that U shape, right? Okay, lastly. This is where dy dx, or f prime, is what's dy dx there? Positive, because positive slope. d2y over dx2, or f double prime, is also positive. So if you were asked to sketch What does a graph look like if it's slope negative and concave up? You'll sketch this portion of the graph. Okay. If you're asked to sketch what does f prime positive and f double prime negative look like, it'll be this portion of the graph. So there's 4 ways that the slope and concavity can interact with each other, and they're going to create 4 different ways that a curve can look. Okay, page 9, guys, page 9. Did we do number 4 together? No, okay, let's do number 4. So if g of x is x cubed minus x minus 1 on the interval from -1 to 2, determine if mean value theorem can be applied. So mean value theorem requires 2 conditions, right? What are the 2 conditions? Continuous differentiable, right? There's no, as long as you can make the first condition pass, the second condition will pass along with it. Okay? I won't give you one where it'll pass the first one, but not the second one. It's a polynomial, no vertical asymptotes, nothing to check. So our function is continuous and differentiable. Let's practice writing it out because we want to make sure that we know when to use brackets and when to use parentheses. Continuous is with what? Brackets. And then differentiable is parentheses. I'm looking for your conditions, not only just you got to write continuous with brackets and differentiable with parentheses to earn that full credit with your conditions. So here is mean value theorem. Mean value theorem has the same formula as Rolle's theorem. So what is this describing? How would you describe what you're doing here? This is slope, right? So to find slope, we have to do what? What do you do with the -1 and 2? Plug in and find the y values. Yep. And once you have your full order pair, once you have 2 sets of order pair, you can find the slope. Right? And all this is done before the derivative, right? If you start introducing derivative into as your first step, you're going to start plugging -1 and 2 into derivative. We don't want that, right? We want to find the order pair at the function level, not at the derivative level. Right? Slope between the endpoints, change in y over change in x. That's your average rate of change. Six minus 3 equals 2. 6 over 3 is 2. So this is my average rate of change. This is the slope between the endpoints. This is how we're going to tell the derivative what to look for. So we know that this curve at some point is going to experience a slope 2, and the derivative is going to help find that location where a slope 2 is going to occur. So now we can find the what. Find the f prime, which is what? The derivative, right? And what's our derivative? Power rule. 3x squared. Excellent. So how do we involve the 2 with our derivative? Where do we plug the 2 into? This goes in for my g prime, right? This is a slope information. This is not x value information. So this goes in for your slope variable, and then you're solving for x. Take the square root, plus or minus shows up. So I get x equals 1 and x equals -1. Are both these valid solutions? Are both these valid locations for mean value theorem? Where do our values have to live? In between the interval, right? In between the interval, which means, which do we remove? -1. Okay, it's right at the endpoint, not close enough. It's got to be between. So C is equal to 1. Okay, your quiz will look a lot like page 9 and 10. I think tomorrow during the help session, I'll probably work through the rest of page 9 and 10, and then maybe pick out some problems from worksheet 4 as well. So you guys have, it'll be front and back. The quiz will be front and back. It'll be basically one of each type of problem. Okay. Make sure you bring your calculator. I'll send out a reminder tomorrow morning is your quiz help session 7:15. All right, come get your phones. Okay, great. All right, you're caught up. Thank you. Maddie, I've got everything from you.
Oh,
Good.
really?
Yeah. Okay, here, I'm working. Okay, so what is your